states of matter, ice, becoming liquid. Very cold liquid. This is very hard and rocky. Oh, goodness. Oh, I think it's a steak. It's a steak. Oh my goodness, it's a steak. Oh my goodness, it's a steak. Studying the water, yes, it's lots of water, it's wet, it's all over the place here. Goodness gracious, I wonder what it actually is, but it's just relaxing. All right, make some noise for science on stage. Come on, everybody. We are ready to get started today. All right. And let me see your cards. Let me see your cards. You have your cards with you. All right. We're going to learn about science today, states of matter, from our two stars of the show. We have Dr. Boom and Professor Matters. Give it up for them. Where is Professor Matters? There he is. Let's give a round of applause.
Thank you. And welcome. Welcome to Chatter About Matter. I'm Professor Matters. And have you ever wondered what the material, the matter that you interact with every day is made from? Have you ever concerned about yourself with that they're made of tiny little atoms? And those atoms are made of even smaller particles called quarks. Well, it's a pretty amazing thing. The lightest elements, hydrogen, came from stars at the beginning of this universe. And in star formation, with enough hydrogen there, fusion processes occur that cram those hydrogen atoms together to produce even more elements. And as the stars evolve, they actually explode and they produce even more elements. So what does that have to do with states of matter and you and me? Well, we're made up of elements that are on this periodic table. We're made up of atoms that are there, and those atoms originated either at the beginning of the universe or in star formation. It's pretty cool to think that you are made of star stuff. Let's take a look at how we can add energy or remove energy from states of matter and change them into another state as we look at solids, liquids, gases, and plasma, and we chatter about matter. All right, Dr. Boom. Dr. Boom, where are you?
Professor, I have it. Professor, I just came from the Pizzazz lab, and I just found this stuff that I had sitting on the shelf. You should see it. It's glass that does not break. It's unbelievable. If I hit it with a hammer, it won't break.
Glass that does not break.
Wouldn't that be great? Glass does not break?
Well, so that's your hypothesis, right?
Yes, it's my hypothesis.
And scientists like to make hypotheses about observations they make, but then they like to make a test or do an experiment or make a measurement.
Oh.
I have a little gizmo here that can test your hypothesis.
It won't break because the script, I wrote the script on here for the show.
This is like a hammer.
So let's see. If I put it here.
Okay, you've got this in a plastic bag.
Okay, so don't break it because the script's on there. Okay.
Well, no, of course. It's unbreakable glass.
I'm going to go get something else for the next demo.
Okay.
So you be careful.
All right, I will. So shall we try it while he's not here? Uh-oh. Uh-oh. Uh-oh.
What did you do to the script?
Why did you write the script on the unbreakable
well, it's
glass?
unbreakable. It's supposed to be unbreakable.
Well, but it's not unbreakable.
Oh, well, I guess it didn't work.
Well, we have to change our hypothesis.
Okay.
And maybe you need to go back to the pizzazz lab to make a new
There
formula.
goes our $1 million. We were going to make $1 million on this.
Is that all?
Well, just maybe 10 million.
maybe $10.
Oh.
Okay. All right. So, Dr. Boom, we were wondering about solids.
Solids, yeah. Solids, crystals,
So
chemical bonds.
we'll talk about all that in just a moment.
Okay.
All right. There's our little introduction to solids. So solids are all around us. Solids make up this fancy hammer here. Solids make up lots of things. And the solids are made of atoms that are held together by chemical bonds. The bonds are between electrons, between atoms. They hold on very strongly. Those bonds can take a lot of pressure from the outside, a lot of stress. They hold things together. There are lots of different arrangements that can be made, that nature has made. Lots of different, yeah, there we are. Lots of different molecules are made by putting atoms together. I have a little ethanol one here, which is ethyl alcohol. I have a little benzene one here. Oh, this is sodium chloride. So these are models that humans have made so that we can kind of point and discuss and think about.
So sodium chloride?
Sodium chloride.
Where do we find sodium chloride?
It's a rock that you would eat.
Do you guys know where sodium chloride is?
It's table salt, and it's a rock that you eat.
Oh, eat?
You eat a rock.
Can you imagine eating something like this?
Well, they're much smaller, and of course, it's a little different than this. But nevertheless, these individual crystals grow to make larger minerals, and he's got some examples of minerals in there, and the minerals make up rocks. Pretty amazing. So we've got atoms into crystalline lattice, into minerals, and into rocks. And then rocks into mountains and the like. Very, very cool.
So these rocks and stuff, they're pretty hard and they don't really want to move, do they?
That's true. On the other hand, something like this, you can make the bonds in here, or not necessarily the bonds, but between the little structures, you can make them stretch if you want.
Oh, so this is like elastic.
You can make them move. This is an elastic band. It's so like a rubber band or a balloon.
This is an elastic solid.
This is an elastic solid, yes. Elastic means you can deform it, you can stretch it, and it goes back to its original shape. We've all seen that with little rubber balls and rubber bands and the like. Oh, what have you got here, Dr. Boom?
Well, I have a little elastic demo here. Now, the first part of the demo, this here is a steel rod.
A steel rod.
Okay? And you can see that it's elastic because it comes back to its original shape when it's pulled down and deformed. But we can put it into the plastic stage. So let's see. Let's do an experiment here. How many weights? So this is one weight. So this will come back to its original shape.
Okay, so you're still in the elastic stage there.
All right, so we'll put one weight in it. Put the second weight in it. Put the third weight in it.
Should he put more in it? Come on, Dr. Boom, let's put some more. More of your little masses in there.
How many more? Let's see. Hold on. It comes back to its original shape. Okay. This is still elastic. Okay. Let's see. There's 2, 4, 5, 6. Will it come back? Let's see. Will it come back? Well, yeah, it will. Let's see what 7 will do. Oh. 8. You want to go for 8? 9. All right, let's see.
Well, we got to
let's see now. Oh, look at that. So it's plastic. It went into the plastic zone.
Yes.
So it went on the curve from elastic to plastic, and then what happens is it would break, right, if we kept going. So I have one here that will, a piece of wood, basically, and it will deform, but it won't be deformed as much as the steel. and it will break before the steel. So
you mean it'll reach a fracture
it will reach a fracture
stage
exactly.
pretty quickly?
Yes, and so
Kind of like your unbreakable glass?
well, you know, science is built on failures, and
you can learn from your failures.
You can learn from them, right? That's what we're trying to do. All right, here we go. I have one weight unit ready to start us out. Ready, 2. Oh, we're doing it.
It's still somewhat elastic.
3. Okay, 4, 5, 6, 7, 8, 9.
There you go. You hit fracture stage. My goodness.
9.
Now, all of these little examples were done at room temperature. That is the temperature of the room that we're in right now. And that's relatively warm. We could heat them up or we could cool them down and we could see something else. We don't have a way to heat them up right now, but Dr. Boone brought some liquid nitrogen from the Pizzazz lab, and he's going to show us what we can do with that. So, what are you going to do, Dr. Boone?
Well, I'm going to pour some liquid nitrogen, if I can find my shield.
So this liquid nitrogen is like the air that we breathe, but it's been cooled down so much, energy's been taken out of it that it's turned from a gas to a liquid.
Well, we're going to run out. Okay, we have some liquid nitrogen in this cup, and I'm going to put this here elastic tubing into it, and let's see what will happen. I need the boomer hammer. Now, as it cools down, you see we have a little geyser here, and then as the geyser stops, it gets more and more solid. So now this tube is really hard. Okay, it's cold, and it's become brittle, kind of like a rock. And so now, if I take this tube away from here,
now how can we test that as brittle or rigid?
We can hit it with a hammer. So now here we go. Ready?
Well, okay, that certainly broke it up. Looks like macaroni now.
Yeah. So when it got warm again, it was actually did not break. So all these little pieces here were fractured just like a rock, just like a piece of glass.
So temperature effects are important for a lot of things. Now we can take energy away from water and make ice and make that rigid as well. We can do that with other little elastic things like a
basketball.
A basketball.
We could do it with a basketball.
A basketball would be good.
I have a miniature basketball right here. Now we can hit this basketball, and it doesn't break obviously because it bounces and it's soft and it's
elastic.
But if we cooled it down with liquid nitrogen, what could we do? Let's see if I pour this out. Okay, so here I have a basketball that's been frozen, and I can hit it with a hammer, my boom hammer. Are you ready? 3, 2, 1. Oh man! So this is as hard as rock.
It's hard until it warms up again to room temperature, and then it'll be flexible again.
Wow.
So different materials have different attributes, whether they're very, very cold, very, very hot, or in between. Very cool. Now, solids, liquids, and gases aren't the only things that we have, or simple solids. What have you got there?
This here is called oobleck.
Oobleck.
Now, are you familiar with oobleck? Okay, so oobleck was Dr. Seuss's thing, and so this is cornstarch and water. And so I made this up yesterday, and it's sitting here flat, and it all flows to flat. And the beauty of it is that it's hard when if a fast object tries to go through it, it stops it. Okay, so it could be used for like a bulletproof vest.
You want to try it?
We're not going to do blow up a reservoir.
Okay.
But I can put my hand under it, and you can hit it with a hammer.
You want me to hit him with a hammer? You ready?
Yeah, just like that. I survived. So turns out that this thing here is a pretty good shield for the forces that are coming out with a hammer. Now, he didn't hit it with a claw hammer thing, and so we're going to put this here, right over here, and we're going to come back to this later in the show, and we'll see how it flowed together. Okay.
Very cool. Now, let's talk about sublimation. Careful, you have the doers right down there, Dr. Boom.
Thank you.
Sublimation, and you can try this at home. Sublimation is when solids go directly to a gas. Now, if you've ever left an ice cube in your freezer for a very long time, you'll notice that it gets smaller and smaller and smaller, and that's because it's going from a solid to a gas. So let me put a little dry ice in here to warm it up, and the solid is going from solid state not to a liquid, but going directly to gas, and that's called sublimation. And we can see that here.
So this is called dry ice because it never melts. It just evaporates.
But don't touch it with your bare hands. There you go. So you can try this at home with an ice cube in your freezer, leave it in there for about a month, check it out, and maybe once a week, it'll be a little smaller, little smaller, little smaller. And that means it's sublimating.
I couldn't resist.
Okay, Dr. Boom, these are things that students may have already seen, but there's more to solids than simply that.
Okay, so I want to tell you about the fifth state of matter. Has anybody heard about the fifth state of matter? No? Well, you heard about the fourth state of matter, right? Plasma. Well, it turns out the fifth state of matter is symbolized by this. It was formulated by Bose and Einstein. They collaborated together in the 1940s, and they theorized what happens at absolute zero. When you take all the energy of the atoms away, and what happens to the atoms, okay? So scientists have done this in like the early 2000s, and they've actually perfected this. And so what happens and what they've observed is that the atoms, they all glom together. So the individual atoms, they all form together, they all go together like a liquid. And they're just in there. And so the individual atoms are kind of like the crystals. They're not individual anymore. They're all like a team, okay? So, but what happens is, as soon as they go just a little bit above absolute kind of zero, let's say we put them in a container, and the container's warm, and then they all just form gas atoms, right? Like this, and they all escape, right? Just like that.
What's all that about? So that's Bose-Einstein condensate. This was your model. This is your model to describe that.
Right. Exactly.
Very good, Dr. Boom.
Always good to have models.
Very good. Thank you. Can you have one?
All right, well, virtual audience, welcome to our Science on Stage laboratory, where we're going to ask some questions, see what you've learned. Make sure you go to this page right here, kahoot.it, put that in the browser, and here is your game pin, so you can play along with us. All right, here's your game pin right here, so you can play along with us. So make sure that you enter this number when you get to this page right here. So go ahead and enter that number there, 5282917, and we're going to play a game to see if you've learned something watching us, all right? And you can also use the link to 6Connects, to the 6Connect site where the auditorium where you came in. You should see a link to be able to connect to our game. So go ahead, and I will wait for our players to join. All right. Again, if you're watching us right now, get on that Kahoot site and play along with us, all right? So here we go. So again, that's kahoot.it, and then you can play along with us, all right? Fantastic. All right, so come along and play with us. All right, that's your game pin right there. All right. If you're watching us online, this is a way for you to interact with us, to interact with the show. All right, thank you, Izan. All right, we'll give you another quick minute to join. Again, you need to go on the Kahoot website or through the link that is on your 6 Connects, and you'll be able to join us for our game today, okay? You could do it one per class. You could do it as individual students, and then we'll play this game, and you'll be able to play it. In fact, even if I go offline, if I go off there, you'll be able to play it and go from there. All right, so we're gonna get that started. All right, get that going. And again, you'll be able to, even if for some reason I go off the air and I'm not here anymore, you'll be able to play it. So, all right, thank you for joining. All right, great. Once again, make sure that you do have that Kahoot.it, and then we'll continue. We'll keep going with this game today. All right, thank you, student Calvin. All right, so again, that is the Kahoot.it is the site. All right, and then we'll get going. All right, yeah. All right, great. Okay, we're gonna get this going, and again, this game will continue playing on screen even if I'm not here to watch you. All right, so let's get going. All right, we'll get this going, and even when I am gone, you'll be able to continue playing with this game. All right, so continue interacting with it, and we'll go from there. Okay, we'll stop it in a second here. All right, we'll be back for a second round. All right, so we will be here again to play with you. All right, so let's go ahead and get this started. All right, and again, if I'm not here, the game will continue on. All right, so here we go. The first question, how can you turn solid ice into liquid water? What's the answer? All right, that's the answer. Okay, still have a few more seconds to answer. All right. Great job. All right, let's go to the next one. And again, you can chime in even if I'm not here online with you. All right. All right, here is the next question. All right, thank you for interacting. Got it. All right, here we go. Evaporation of a solid is called, what is it called? It's called sublimation. Only 2 people got that right. How did we do? Let's see how we did here. All right, we got in our short quiz, we have number 2 right, Izan. Congratulations, you have number 3 and number 2, Benjamin. All right, number 1 spot today, our Kahoot winner is Dominic. Congratulations, Dominic. And then we have a couple students that are runner-up. Thank you for engaging and playing with our Science on Stage show. We're going to be back again. All right, we're going to be back again. All right, great job. All right, let's see a little more things here. All right, let's see how we do it. All right. So, oh man, a lot of people did not get that right. You know that, so obviously the way that you turn solid ice into water is by adding energy, and that's what kind of we saw in the show. They added some energy to something that was solid, and they made it change. And in fact, that's how you change from states of between states of matter. You add energy to the system, and you can change the states of matter. The current question of evaporation of a solid. So they showed that as when you have something solid and it's turning into a gas. You know, the states of matter usually go what? Solid, liquid, gas, right? That's usually what happens, but sometimes a solid can go straight into a gas and skip that liquid part, and that is called sublimation. It's not freezing, because freezing is actually when a liquid becomes a solid, and it's not compression, because that's more of a physical change, not a change to the actual the atoms and stuff in that state of matter. And it's not constipation, because that's when you can go poop. It is sublimation when you turn a solid into a gas. So it's awesome. Pay attention because we're going to have another quiz coming up in just a few minutes, and we'll be right here again at the Science on Stage Laboratory. See you soon.
Hi, I'm Dr. Sean Tang, a plasma scientist, and I work at the D3D National Fusion Facility, which is operated by General Atomics on behalf of the U.S. Department of Energy. It's here inside the D3D tokamak where we push the limits of the control and understanding of a very high temperature ionized gas called a plasma. This is a worldwide effort to pursue fusion energy as a sustainable energy source to produce electricity for all humankind for the next millennium and beyond. My background is primarily in math and physics, but my real passion is in RF heating, which is understanding how we can use electromagnetic waves with certain frequencies to foster heating of the plasma. This is so we can produce efficient fusion reactions so that in the future we can operate clean, environmentally safe fusion reactors to produce electricity to power our lights, computers, hovercrafts, and whatever else the future brings. We need more scientists and engineers to continue this path towards the future, and we hope you'll join us. Let's take a brief tour of where I work and where I hope to see you someday.
So we're inside the D3D tokamak, large vacuum chamber, toroidal in shape, like a big donut. You can see it looks kind of like a donut around. We'll take a walk around.
Today was to help you understand that when people do science, they can make a difference towards the future needs of humanity. I hope that you are inspired to pursue goals that include the betterment of humankind, whether those goals are in science, engineering, mathematics, or social causes. Our future is dictated by the choices we make today. As for me, I hope to see you in a science laboratory soon. I have confidence you can do it. Thanks.
Okay, Dr. Boom. All right, that was good, Dr. Boom.
Yes, sir.
They even had that little video where we work at D3D, National Fusion Facility.
Yeah, they had you inside the vessel.
I was inside there, yes.
That's where 150 million degrees centigrade plasma exists when we operate.
Wow, we'll talk about plasma a little later.
Okay.
Right now we're going to talk about liquids.
Well, I brought the script.
Okay, hold on a minute. Let
I
me
got
move
the
this
script.
over.
I got the script.
Okay, good.
I got the script.
Okay.
Okay.
Oh, I need to get water.
I'll
for
leave
that.
the script right here.
Okay, you put that there.
Yeah. I'm gonna go get some liquid nitrogen.
When you get the other stuff over there, let us know what you're doing over there.
Okay, I'm bringing over the liquid nitrogen. Liquid nitrogen's in this dewar.
Good.
And so I have it with me here. So.
Okay, so what are we doing next?
And we're gonna need our friend Oscar here.
Okay. All right.
What are we doing next? Well, let's look at the script. The script is wet. The script is in this blue water.
Oh,
the script is.
Why'd you put it in my water?
I didn't put it in your water. You put the what? There's a script, and what are we going to do with the script? It's all wet.
Well,
I'm going to put it right here. We'll have to work with the wet script.
Okay, that'll work.
First thing is to dry off.
So water is something that we're quite familiar with.
Yeah.
Water has a certain density.
Yes.
Or mass per volume, or kind of on Earth we could say weight per volume. And I have a brief density column here, or a short density column here. I have the most dense liquid, less dense, and the least dense liquid here.
How do you know this is the most dense?
The most dense because it is on the bottom. It's closest to the center of the Earth here. It has the most mass per volume.
Oh.
And it happens to be Karo syrup, just standard, highly sweetened Karo syrup.
So then this one here is the least dense.
That's the least dense, and this one's in between. So we don't necessarily know what the densities are in a quantitative way,
right.
But qualitatively we can tell that most dense, less dense, and even least dense here.
Wow.
So this is syrup, water, and vegetable oil. Pretty cool.
It is pretty cool. It's so cool that you could make one of these at home.
Yes, easy to do, and you can get other liquids you find out, and maybe you can have 10 different layers there. Pretty awesome.
So I brought some liquid nitrogen again.
Liquid nitrogen?
Yep.
That's at minus 196 degrees Celsius.
Minus 196 degrees.
Wow.
That's really cold. That's so cold you can't even stick your finger in it.
I wouldn't want to put my finger in it.
No, not me either. So maybe we can get some volunteers. No, I'm going to pour some in here. And look at it. It looks just like it's clear. It's like water. I wonder what would happen if we poured some of this in that there density column.
You know, this liquid nitrogen, from a qualitative observation, it looks like boiling water.
It does.
Because at this temperature, that is actually boiling.
Huh.
But I noticed that the water vapor that is cooling down from the air is actually going down. So that means it's quite dense there.
Look at that. Boiling, boiling, boiling.
Cool.
So let me pour some into this baggie.
Oh, you know what?
Yeah.
If we follow the concept that we did here with this density column,
yeah,
maybe we can put some of this
okay, so
script water.
So if so we're going to pour some water into the liquid nitrogen. So is the water going to sink or is it going to float?
Well, let's think a hypothesis. Who says the blue water will go to the bottom, meaning it's more dense? And who says the water will stay on top, meaning it's less dense?
And how many don't know, don't care? Just like our scientists.
I didn't see any hands on that one.
Okay. All right, so here we go.
Let's do the experiment.
2, 1. So we're pouring a warm.
Okay, so what do we observe?
Whoa, look at that. So
water is on the bottom.
Yes.
And that means the water is more dense than the liquid nitrogen.
So
we don't know what the density is, but we know that it's more dense. This is a qualitative thing.
Pour it back into the container. Halloween again.
Very cool, Dr. Boom.
All right. Now what else can we do with this?
Well, I have a balloon here.
Yeah.
This balloon we blew up this morning. It has some air in it, and that air means it's got oxygen, nitrogen, a little argon, a little bit of carbon dioxide, not very much. The molecules in there, the molecules are moving around very, very rapidly, and they're hitting the inside of the balloon with such force that it makes the elastic of this balloon actually stretch out. And if I could remove some of the energy of the molecules in there by cooling them down, so I'm removing energy here, we can actually see if we can condense some of the gas and at least remove their energy so that they're not populating that.
Oh, watch out, don't touch it.
I'm not touching it, I'm being very careful.
Oh,
but you can see this balloon.
Oh.
But now that it's back in room temperature, the molecules inside are gaining energy again, and they're moving around quickly, hitting the insides of the balloon. There's a little bit of liquid in there, but it's going away quickly.
So you didn't take any atoms out of the balloon? You didn't put any atoms in the balloon?
That's correct.
It just
no atoms
changed
or molecules.
states of matter?
Nope, we just changed the states of matter.
You took, oh wow.
From gas to a liquid.
Right.
By removing their energy.
Well, we could do a reverse of that. We could add energy to this liquid nitrogen, and we can turn it from a liquid into a gas. And so we can do that with this thing called Oscar. Oscar's waiting to come out. And so here we go.
So you've got the liquid. We're going to heat it up just using room temperature, but we're going to capture the gas. Capture the gas that's formed, and you'll be able to say hi to Oscar. Okay. Everyone wave to Oscar. Now you can wave hello, or you can wave goodbye. Goodbye.
See you later, Oscar.
Goodbye. All right. Now how would you, can I get a volunteer up here to put their finger in here? No, hold it. Look at all those volunteers.
No, don't come up.
No.
Put your hands down, you can't come up. If I put your finger in here, how long do you think it would take to freeze and I could break it off? You would be missing your finger forever, okay? If I did that with my finger, I'd be missing it forever too. So what I did is I talked to my friend over at UCSD Medical Center, and they don't use all the fingers from the cadavers, right? So they have dead people that they test operate on. So he loaned me a finger. I have to send it back.
You have to send this back?
It's a finger, and I know this guy's name. And so let's see, I froze it and it's here. Watch, I'm gonna pull it out. I'm gonna pull it out, here it comes. Here it comes. Okay. This guy's name is Oscar Meyer. Okay. Now this is a demo finger. Okay, so it's a hot dog. Okay, but just imagine it could be just like yours. So what can we do with this finger? Well, we don't have enough for hors d'oeuvres, so we're gonna have to break this up and watch. So there you go. Now we have enough for Oscar Mayer chips. You see that? Now, if you watch Terminator with the liquid metal man, and when the truck dumps the liquid nitrogen on the street, and liquid metal man gets frozen, that's what this is like.
Now you can try this at home as well, but I bet if you freeze a hot dog in a bag and try to break it, it will only break once, because your freezer is nowhere nearly as cold as this liquid nitrogen. So now, are volcanoes on Earth hot or cold? On Earth, volcanoes we think of them as hot, right? The hot gases down below erupt and they spew out liquids and gases and solids. That's on Earth, but on moons of other planets in our solar system, there's actually very cold volcanoes. And they spew out ammonia or methane, liquid ammonia, liquid methane. We have here the coldest volcano on Earth. And Dr. Boom is going to show that to you. It's a very simple thing. We have some soapy water down there, and Dr. Boom is going to expand that soapy water up to this line, this second line right here, by pouring in some liquid nitrogen.
You ready?
So, we're ready.
3.
Countdown. 3, 2, 1. Nicely done, Dr. Boom. And it is a volcano. I see gas erupting. There's certainly liquid around it.
Oh, yeah.
And if I put my hand in the volcano, I can pull out some solid. It's just ice, but it's gases, liquids, and solids right here in the coldest volcano on Earth.
No plasma, though.
Well done, Dr. Boom.
All right.
Well done.
Good job.
All right.
Hi, my name is I'm Tara, and I'm currently a third-year biomedical engineering major here at California Baptist University in Riverside. Today I'm here to talk to you about the different stages of matter that plastic goes through when being 3D printed. It's pretty cool, actually. So plastic turns from a solid into a liquid and then back to a solid product again. The way this works is the filament is fed through a part of the 3D printer where there's 3 different components. There's an extruder, a press, and a heating rod. The extruder feeds the filament through the heating rod, where it's then pressed down at its liquid form when melted at 215 degrees Celsius. This comes out and is printed out on a mat and results in a solid product. The cool thing about plastic being melted down is you can combine it with different materials. These materials can include other types of plastic or metals such as carbon fiber. And it can result in products like this frog, this trophy, or it can have a bunch of different parts that can be clicked together and create items like this hand. It works similarly to a glue gun, where the solid glue stick goes through the heating rod in the glue gun and is printed out as a liquid. This liquid, after some time of cooling, turns into a solid product, and that's the 3 stages of matter it goes through. Thank you so much for listening to me today, ladies and gentlemen. I hope to see you in the STEM field.
Hello, I'm James Hamrick. I'm a senior at Cal Baptist University where I study mechanical engineering. And today I'm going to talk to you about states of matter. The way I'm going to illustrate that is by using a refrigeration cycle. So behind me I have a standard AC unit that you'll find in most residential homes. There's 4 components to an AC unit. You have the compressor, the condenser, the expansion valve, and the evaporator. Those 4 things are what's used to change states inside there to be able to make it cold. So starting out, we're going to talk about the compressor. The compressor takes a low pressure gas and makes it a high pressure gas. After that, it gets passed through the condenser. The condenser will take the high pressure gas and have a state of matter change where it will make it from a high pressure gas to a high pressure liquid. After that, it will go through the expansion valve. The expansion valve will take it from a high pressure liquid to a low pressure liquid. After that, you'll come through and go through the evaporator. The evaporator will have another state of change where it'll go through a low pressure liquid to a low pressure gas. Once that's done, it goes back through the compressor, and that completes the refrigeration cycle. Thank you. I look forward to seeing you in STEM.
Very cool, very cool. You see that 3D printer that young student was making?
I did.
That was very awesome. 3D printing is really, really popular now. You can do a lot of things.
Yeah, it'd be good to 3D print concrete and print a house, you know?
It would be cool, yeah, they do that. So now, Dr. Boone, we've talked about solids and liquids.
Yes.
We're going to talk about gases and plasma.
Yes.
Let's get a few things set up here.
You need a table. And I brought my script here, and we're going to put my script where you will...
Okay, so let me get this. I want to show them, before we get off too far, I want to show them an example of gases to plasma.
I'm going to put the script right here, and I'm going to go get the first demo.
Okay. So, I have a little high voltage coil here. If we can have the lights off, and I have a little glass tube. And what we can do inside of this glass tube is some gas. And if I bring this high voltage coil up to it, we can actually light this up. Okay, we can light this up with a little spark. This is a little Tesla coil, and there's another one in here. And in these cases they colorize them. You and I know these as neon lights. And let's see what else.
Okay. Hope you have been protecting my script because we need my script to see what we're going to do next.
Yes.
But this is the next thing.
Here, I got your script right here.
What happened?
Yeah. No, that's your script.
My script? Yeah. My script is always being screwed up because of something.
All right, let's move on, Dr. Boom. Don't worry about that.
Okay.
We saw a density column earlier, the liquids. We had 3 different liquids, 3 different densities. And we can easily observe that they're floating. One is floating on top of another, on top of another. We're going to do the same thing here, but we're going to use a gas that you won't be able to see, but you can see the effect. You know that if I held a helium balloon here and let it go, helium is less dense, it would rise. If I held a standard balloon here and let it go, it would fall because of the mass of the elastic on there. What we're putting in here is a little bit of very high density gas called sulfur hexafluoride, used by electric companies as an electrical insulator. And what we're going to do is see if we can actually float these balloons on top of that sulfur hexafluoride. Sulfur hexafluoride is non-combustible. It doesn't burn or anything like that, so it's relatively safe. Hey, he did that. So these balloons are actually floating.
Oh, don't let them get out.
On top.
Oh, they're not leaving.
Of the sulfur hexafluoride. That's pretty cool.
Nice. So now, sulfur hexafluoride does not support burning things. So if I light this candle that's in my grandmother's candle holder from like 120 years ago.
Thank you, Grandma.
Yeah, we're going to see how far we can go down into the sulfur hexafluoride before the flame goes out. Okay, so that's where the sulfur hexafluoride. Oh,
it's
wow.
Right at the surface.
It's right at the surface.
It's right at the surface.
So if I take the flame and run it down, and I stick it in real fast, ready? Let's see if it goes fast. Oh, no, I don't want to do it too fast. If it goes slow, it goes boom out. Oh, look at that. So it goes boop out.
So that's telling us the sulfur hexafluoride is right up to the top here.
Yeah, it is. So there's the smoke is inside, but that's expected. Okay.
So
there you go.
Here we are bouncing these balloons on top of a more dense gas. We can't see it, but we can see the effects of it. And so very often scientists can't see things directly, but they have to look at indirect observations. So what have you got here, Dr. Boom?
Well, this here is my cheap plasma bulb. Of course, you have to have a Tesla coil here, a handheld Tesla coil. And so if we have the lights out, please. The lights out, yeah. Well, I don't know if you can see this. There's the plasma inside. This is a nitrogen plasma, so they put nitrogen in these bulbs. And this is an incandescent bulb. You can't get these. These are becoming very rare. It's called the Edison bulb. It has a filament in it. And so there's the plasma inside. Can you see that?
There we go. Yes,
there we go.
Much better.
So
the gas that's inside of that bulb, these are standard incandescent bulbs, or Edison bulbs we call them, is nitrogen. But there's also other gases that are used. Neon and argon are used for a lot of things.
Now you showed them this one, right?
Nope.
No? Okay.
No,
so
I didn't show them that.
This is plasma. So plasma is formed when we energize the atoms inside and we strip away the electrons. And so it's gas now, plasma, gas, plasma, gas, plasma. We can switch it back and forth very fast. Okay, this is a neon tube. This one here is filled with argon. Argon is another inert gas and it has a blue color. And if we put these two together...
One of the characteristics of plasma is because it's been ionized, there are electrons that can move, and it can act like a wire and carry electricity.
That's right.
Very cool. So at our work, we operate a very large plasma, over 100 million degrees temperature.
Right, and the plasma inside these tubes is about 20,000 degrees, well, the neon's 20,000 degrees centigrade. These are about 12,000. And so it's quite warm, the electron temperature. So this is the plasma that goes on your fluorescent tubes at home or at work or at school. And the coating is what makes the light be white light.
So Dr. Boom,
Yes, sir.
I brought something from the Pizzazz Lab.
Oh, yeah, we have more in the Pizzazz Lab, huh?
Like. Remember his little handheld Tesla coil? Well, here's a tabletop Tesla coil. And I think it puts out, what'd you say, 10,000 volts or something?
250,000 volts.
250,000 volts.
250.
Voltage is a measure of energy. And we are going to see, here, Dr. Boom, you want the controls?
Okay, thank you. All right, are you ready for this? Okay, here, I'll give you a little teaser.
Very nice, Dr. Boom.
So you can see I have like a lightsaber.
Dr. Boom, that matches your shirt.
Yeah. Now this is a fluorescent tube. What happens if we put the neon tube or the argon tube on it? Let's see. There you go. How about the argon tube? Can we light this one up? All right.
Sorry, that was neon again.
Oh, that was neon.
Let's go
yeah,
with
sorry.
argon.
Okay.
Now, Dr. Boom, I have another thing from the Pizzazz Lab.
Yeah, what do you have?
It's a little something I put together this afternoon.
Yeah. Oh, okay.
We call this fanfare.
Fanfare.
And we'll see if we can light them all up.
Okay, that's pretty cool.
Very cool.
Now, what would happen if let's say we were on another planet, and we had a large thunderstorm, and we don't know what's going to happen if we go down to the planet, and we don't know if we're going to survive. So we'd have a little spherical spaceship here, and we're going to see what happens. Okay, we're going to put it down, we're going to check it out. Oh, whoa, that was flammable.
Oh, Dr. Boom, I don't know if I want you driving my spaceship.
We want to drive our spaceship down to that planet. Okay.
I'll take care of this.
No. The longest plasma device. Right? So we have two more demos for you.
Yes.
So we need our helpers. And so we have the longest plasma device in Riverside. So today. And so we brought it with us, and we're going to light it up from one end to the other. And so lift it up. Lift it up. Up. Okay, there it is. So it goes from one end to the other. So I'm going to take this Tesla coil, and I'm going to light it up from one end to the other. You ready? Here we go. 1, 2, 3, 4, 5, 6.
No. Dr. Boom,
what?
no.
What?
You said this is the longest plasma device in Riverside.
Right.
What we need to do is light the whole thing up at one time.
I'm going to light it up. Ready? 1, 2, 3, 4, 5.
No, Dr. Boom. By the time you get to number 3, number 1 is out.
I wasn't watching that.
Well, we got to do this right.
Okay.
Maybe there's something wrong in the electrical system.
Let's see. I can get closer. Okay, this is maybe if I get towards the center here.
Well, maybe there's something wrong with the electrical system.
I don't know. There's something wrong here. I can't. Oh, holy smokes! Did you see that?
I did.
I think I found the problem. Here it is.
You found the problem.
I think there we go.
There they go. They're all lit up.
Yay,
Very nice.
we did it. All right,
well
once
done.
again.
Well
Yay.
done.
All right.
All right, and then, again, that's an example of
Thank you very much.
Carrying electricity.
Thank you very much for our helpers here. All right. So we have one more demo for you before we say goodbye. And so this is called a combustion demo. And so what we do here is this is about ICE engines, internal combustion engines. We have the next slide, please. No, this is not the one. The engine. Yeah, there we are. Okay. So this here is a demo of an engine. Now you see the red spot here. When it goes up, the piston goes up, that's a spark, okay? And that's a plasma. So the plasma is a spark. And so I have two screws here in a bottle. I have a combustible fluid in here, and there's a cork in the top, and you'll see what happens when I ignite this. Are you ready? Are you ready? Can we have a countdown? 3, 2, 1. Whoa. That's pretty cool.
Dr. Boom. Dr. Boom.
What?
I was at the Pizzazz lab and put something together.
Oh. Oh, wow. What?
And so this is just like your other one, but bigger with more pizzazz.
This is like a 10-cylinder engine. This is really cool. Are you ready? 3, 2, 1. Oh. All right.
Thank you, Dr. Boone. Thank you.
All right, everyone. That was the science on stage. Let's give it up for Dr. Boone, Professor Matters. All right. Awesome, awesome, awesome. Next year, join us next year. What are we doing next year again? We're doing
surfing the electromagnetic spectrum.
Electromagnetic spectrum. Thank you, everyone, for coming today. Make sure that you join online. And you'll see a lot of QR codes on the wall. Join online, and you'll be able to watch the show again and interact with lots of things. Make sure you got your cards with you. Everyone has their cards still. All right. Thank you for joining us today. Thank you to D3D and General Atomics and everyone that made the show possible. Bombardier in the back.